Let us solve this question. A rigid horizontal bar AB hinged at A is supported by 1.2 meter long steel rod and 2.4 meter long bronze rod. Both rigidly fixed at the upper ends. A load of 48 kN is applied at a point that is 3.2 meter from the hinge point. The areas of the cross section of the steel and bronze are given as 850 mm square and 650 mm square respectively. We have to find the stress in each rod and the reaction at the pivot point. The modulus of elasticity of the steel is 205 gigapascal and that of bronze is 82 gigapascal. So this is a question of bars of composite sections in which we are given a steel and bronze rod which are supported by a long rigid bar, this bar AB, and a load of 48 kilonewton is applied at a 3.2 meter away from this hinge point. We have to find the stresses developed in steel and stresses developed in bronze, and also the reaction at A. What is the reaction developed at this point, hinge point A? Suppose the reaction is RA, so we have to find the reaction also. So let us solve this problem. In this question, there is given a horizontal bar, rigid horizontal bar. The word used is rigid horizontal bar AB, and at which two steel bars are fixed like this at upper end. One is steel bar is this of length 1.2 meter and another is bronze bar of length 2.4 meter. And we have to find out what is the stress applied in steel and stress developed in bronze when a load of 48 kilonewton is applied at section point B at a distance this meter, right? This is around 3.2 meter from the hinge point and this is hinge at another point, right? And the area of cross section of steel is given, area of cross section of bronze is given, E of steel is given, Young's modulus of elasticity, and Young's modulus of elasticity of bronze is also given. Length of the steel bar and bronze bar is also given, and a 48 kilonewton load is applied at the end B of this rigid bar. So as this is rigid bar, there will be no deflection, curvature in this bar. It will be directly come like this, straight line. It will remain straight. After deflection, it will remain straight because this is a rigid bar, right? So this is given that this is a rigid bar. So I am writing here rigid bar, right? And when there is a deflection in this rigid bar, and this is it will remain straight, right? So there will be deflection in steel and bronze, and the reaction will produce in steel in upward direction like this. This is reaction in steel, and also there is reaction developed in bronze at this supports, at rigid supports, this A and B, these points. Suppose this is C and D. So at C and D there will be reaction developed in steel and bronze, right? So we have to find out what is the stress developed in steel and what is the stress developed in bronze. So when a 48 kilonewton load will be applied, rigid bar will be deflected in a triangular way like this, right? So after deflection, it will remain straight, and the condition will be like this. It will become like this. This is the condition of the rigid bar after the load is applied. This is the condition, right? And there will be deformation in steel. Deformation in steel, you can see here, this is the deflection in steel, delta L in steel, and there is deformation in bronze, like this, So this is a deformation in bronze, right? So this point, suppose F become F dash, and this point, suppose G, will become G dash, right? And this deformation is not same. There is some relation between these two, but this is not same, right? So this will be the deformation in this steel, and there is some deformation in bronze, right? So delta L in bronze. So first we have to find out what is the relation in these two. What is the relation in these two? This we have to find out, right? And you know that this is a hinge point. This is a hinge point, and the moment of the forces at hinge point is 0. So the moment may be clockwise or anti-clockwise. The sum of the moments of the at hinge point, sum of the moments at hinge point will be equal to 0, because this is a hinge and hinge is free to rotate, right? So that's why the sum of the moments of the forces, sum of the moment of the forces will be equal to 0, right? So this concept we are going to use. So the moment at point A, I am writing sigma ma equal to 0. So here what is going to happen is, first of all, let us find out what is happening in the relation between delta LS and delta LB, right? So how to find out the relation between delta LS and delta LB? This is our rigid bar before deflection, and this is our rigid bar after deflection. This is rigid bar before deflection, AB, and after deflection this is B dash. So this point is B dash, right? And this point is F dash. The deflection is steel, F dash, and G dash is the deflection in bronze. G dash is a deflection in bronze, right? And this is delta LS, and this is delta LB, right? Now there are two right angle triangles. One is AF dash and another is AG dash, right? And these distances are also given: 0.8, 1.6, 0.8. So this is 0.8, this is 1.6 meter, and this is also 0.8 meter. This distance is also given, right? So you can see here that this triangle AF dash and this AG dash are similar. So triangle AF dash and AF dash and AG dash, A and triangle AG dash are similar triangles, right? These triangles are similar. So these two triangles are similar, AF dash and AG dash, right? For we can use the properties of similarity that base of these two and the perpendicular of these two will be in the same ratio. So AG upon AF must be equal to F AG, so GG dash upon FF dash. The ratio of their base and the ratio of their perpendiculars will be same, right? So AG by AF will be equal to GG dash upon FF dash. What is AG? This is the distance. 0.8 plus 1.6, this is 2.4 meter. So this is 2.4 upon AF. AF is 0.8. That must be equal to GG dash, which is delta L in B, upon FF dash, this is delta L in steel, right? So you can see here this is 3 times, so delta L in B is 3 times in delta L in steel, right? So delta L in B is equal to 3 times delta L in steel. So this relation we have obtained from this, right? This is our equation number 1. This is very important relation we have obtained from this. Now another is we want to find out the reactions first. After finding the reaction, we can find out the stress in steel and bronze. So how to find out the reactions? Reaction can be found out by taking the moment of all the forces about point A. The force, there is some reaction also at A also, RA. The reaction at A, RA also, and we have to find out RA, the reaction at A, right? So there will be some reaction at RA also, because and this is also a support, right? So reaction at Ra, Rs, Rb, three reactions are there, and a 48 kilonewton force is applied here, 48 kilonewton, right? So these are the forces. There are four forces basically: Ra, the reaction at A; Rs, and the reaction of the steel; Rb, the reaction of the bronze wire; and 48 kilonewton that is applied at point B. And due to these forces, the moment of all the forces about A will be equal to 0 because it is a hinge point. So because it is a hinge point. So take the moment, taking moment of all the forces about A. So what are the forces? So forces are here, this is our A point, and this is Ra. The reaction of steel Rs, bronze Rb, and the force applied 48 kilonewton. So take the moment of all the forces about A, and that will be equal to 0 because it is a hinge point. So moment of all the forces about A will be equal to 0, isn't it? And the distance is given to us 0.8, 1.6, 0.8. This is 0.8, 1.6, and 0.8 meter. So take the moment of all. The moment of Ra will be equal to 0 because it is at the same distance. So force, what is moment? Force into distance. So distance is 0 with this. So Ra into 0, Ra multiplied by 0, no distance, plus Rs multiplied by 0.8, and let us take anti-clockwise as positive. We are taking anti-clockwise moment as positive, right? So Rs multiplied by 0.8, so this is positive. Rs multiplied by 0.8 plus Rb multiplied by 2.4 plus Rb multiplied 2.4. This is a reaction of B, Rb. The moment of Rb about A, and the moment of 48. This is total distance is 3.2. So 3.2. So this will be minus because this is clockwise. Minus 48 multiplied by 3.2, and that must be equal to 0. So we will get a relation. We will get a relation between Rs and Rb. First relation we have already obtained, delta Lb is equal to delta Ls. So second relation here we are getting. So there will be a relation. You can find out that this is Rs, this Ra will become 0 because it is multiplied by 0 because there is no distance of A, it is acting at this point only. So there will be a relation between Rs and Rb. What is that relation? You can find out. So Rs plus 3Rb, you will get here, solve it, and you will get Rs plus 3Rb. Rs is the reaction at steel and Rb is the reaction at the bronze. Rs plus 3Rb will be equal to 192. And we are taking kilonewton, so this is in kilonewton basically. So this is another equation, equation number 2. And one equation is this, delta L is equal to 3 delta Lb. This can also be converted into forces or reactions by using that formula which we are using for deformation, that delta is equal to PL upon AE. PL upon AE. So what force is acting at steel? That is the reaction at steel, Rs. And what force is acting in bronze? That is the reaction at B, Rb. So Rs and Rb are the forces acting in steel and bronze, right? No other force is there. So Rs and Rb are the reactions at B. So we can apply from 1 we can write that delta Lb is basically Rb L of B upon A of B into E of B. That should be equal to 3 times deflection in steel. What is the deflection in steel? PL upon AE, the reaction in steel, length of the steel, area of steel, and modulus of velocity of steel. So that must be equal to Rb. Rb is unknown to us, so Rb we have kept it as it is. Length of the B, length of the bronze, that is 2.4. So 2.4 upon area of bronze. What is area of bronze? Where is area of bronze? This is 650 given. So 650 multiplied by E of bronze, 82. No need to change the dimensions because they will cut, we can cancel the from left and right. 3 times RS multiplied length of steel is 1.2 meters, 1.2 meters divided by area of steel is 850 multiply E, this is for steel 1.2, 850, and E of steel, that's it 205, right? So by this you will get another relation between RB and RS, and two equations can be solved and you can get the reaction at RS and RB, right? So again you will get a relation between RS and RB, that RS is equal to you will get the relation that RS is equal to 2.179 RB, 2.179 RB. This is one more relation between RS and RB, and this is equation number 3. Now we have two unknowns, RS and RB, two equations for solving these, and it can be solved. Two equations, two unknown, it can be solved. So on solving 2 and 3, use your calculator to solve, and on solving second equation and third equation, you would get the RS as 80.78 kilonewton, because we are taking in kilonewton, right? So 80.78 kilonewton, this is RS, and RB is 37.1 kilonewton. 37.1 kilonewton. This relation you will get, this equation, this final result you will get for RS and RB. But we have to find out the stress in RS and RB. How to find out the stresses in RS and RB? You know the stress is force upon area. So force we have calculated, reaction in steel and reaction in bronze. These are the forces acting on steel and bronze. So by this you can find out the stresses in steel and bronze. So sigma S will be equal to RS upon area of the steel. That is equal to RS is 80.78 divided by area of steel. Area of steel is 850 millimeter square. So 850. The answer will come in megapascal because this is in millimeter square. So sigma in steel, after solving, you will get 95 megapascal. 95 megapascal. So this is your one of the answers. 95 megapascal, right? So sigma steel we have obtained is 95 megapascal. This is one of the answer, 95 megapascal. And sigma in bronze will be equal to the reaction in bronze and the area of bronze. So that will be equal to reaction in bronze. Reaction in bronze is 37.1 kilonewton. So this is 37.1 multiplied by 1000 divided by area. Area of bronze is 650 millimeter square. Keep it as it is so that the answer will come in megapascal. So answer in megapascal will come out to be, sigma B will come out to be 57 megapascal. 57 megapascal. This is our another answer, right? So I am writing here sigma S as 95 megapascal and sigma B as 57 megapascal. This is our answer which we have to find out, right? These are the answers, right? Next is, what is the reaction at A? What is the reaction at A? This we have to find out again. So how to find out their reaction at A? Finding the reaction at point A, right? So I am rubbing some part here so that I can use this part for further calculation to find out reaction at A. Finding the reaction at A. Now, what are the forces acting? What are the forces acting in upward and downward direction? If the body is in static equilibrium, if the body is in static equilibrium due to these forces, then the sum of the forces in vertical direction should be equal to 0. So sum of the forces in vertical direction should be equal to 0. So what are the forces in vertical direction? RA, RS, RB in upward direction. So RA plus RS plus RB, and that should be equal to RA plus RS plus RB should be equal to 48. The force in upward direction and the forces in downward direction, that should be equal to 0. And we have found out already RS and RB. So RA will be equal to 48 minus RS minus RB, and that is equal to 48 minus 80.78 minus RB is 37.1, right? So when you solve it, you will get RA equal to RA, the reaction at point A, equal to minus 69.85 minus 69.8, nearly 85 kilonewton, right? What this minus sign shows? This minus sign shows that the direction of reaction at A is not upward, it is downward actually, right? So the reaction is basically downward, not upward. So basically RA will be equal to, in magnitude, 69.85 kilonewton, and this is downward direction, downward, right? So actually this is downward and not upward. To make it positive and arrow shown is downward, that is the reaction is basically downward, and opposite to the reaction we have chosen, and the direction we have chosen, this is opposite to that. So this is the last answer of this question.